Okay, today we're going to be studying spectroscopy, but before we get into that, let's just remember Isaac Newton. Some 400 years ago, there was a plague, so he just secluded himself to his farm out in the English countryside, and while he was there, he invented calculus. He invented physics. He used those inventions to figure out the laws of gravity. And made all kinds of other inventions. The telescope, right? We learned about. In fact, we use a telescope in our lab, right? It's called the Newtonian telescope. The basic design after him, using mirrors. So yeah. So the lesson is, during this time when we're sheltered at home, use your time well, right? Newton was one of the greatest geniuses of all time, so be like Newton, right? All right, so we're going to be studying spectroscopy. What is spectroscopy? The camera's shaking, poor production quality, my life is miserable. Yeah, it is. All right. Back up a bit. All right. So we all know pretty much. Oh, let me do this a little bit more. Okay. So we've already studied light quite a bit. And we know you put light through a spectrum, right? Or just light coming from the sun, or the visible light that we can see, right? Roy G. Biv, red, orange, yellow, green, blue, indigo, which doesn't really exist, but they say it exists, violet, right? Roy G. Biv. These are longer wavelengths, shorter wavelengths, right? It's the spectra coming from the sun, right? But we're going to be learning about spectroscopy, which is the study of the spectra. Now, it was discovered some time ago, some long time ago, that the spectra wasn't just this continuous spectra. Continuous spectra means it's just there's no breaks in it, just a continuous spectrum. It was discovered some long time ago that there were actually dark lines in the spectra. If you use very fine prisms, more sophisticated instruments, what they found. Is there a better one? Okay, so what they found was that hang on, I got one for the whole sun here. Maybe I don't. All right. So what they found, here's just an example. What they found was that there were breaks. You had red, and then there was a black line. And then you're going orange, there's black lines. You green, black lines are like, what is going on there, right? What is happening? So that was a real mystery. Eventually what they figured out was that the elements were absorbing certain wavelengths of light. And therefore we on Earth were missing little bits of wavelength from the sun. So we have this spectra coming from the sun. Well, here's one of the whole sun. This is what I was looking for earlier. I knew I had it. Okay, so this shows the sun, right? So here you're going red, yellow, green. There's all these marks where wavelengths are missing. Like, what is going on? There's thousands of them, right? So you have wavelengths coming from the sun, but there's breaks in it. Then there's another break and another break where wavelengths were missing. That was a mystery. Eventually what they figured out was that the elements were absorbing certain wavelengths, and that's why we weren't seeing them. Well, we already talked about this. Remember how ozone in our atmosphere absorbs in the ultraviolet? Yeah, well, it turns out that the sun, so inside the center of the sun, it's thermonuclear fusion. We're going to get into that later. But at the surface of the sun, it's about 5,800 degrees Kelvin, but that's still way cooler than the center. And those elements at the sun's surface, they were absorbing the wavelengths as they were leaving, right? And that's what we're seeing. Now what happens is that it absorbs the wavelength, and then sometimes later it re-emits it, but those molecules are all moving around, so it can emit them into any direction. But coming from the sun, as it's on its way to Earth, it gets absorbed. So we're missing those pieces. So how does that happen? Well, we're going to get into that. Guess what? We're going to talk about that. We're going to talk about that. Okay, so we all know that, so here's a hydrogen atom, right? Hydrogen has one proton and one electron, right? Hydrogen is the most basic, is the most basic element. So we all learned, yeah, at the center you have the nucleus. For hydrogen there's a proton, it has one proton, one electron. For helium there's two protons, two neutrons, and then two electrons, and you go on, boron is 5, and it continues, right? Well, what happens is that hydrogen's sitting here, so we're just looking at this one, it's sitting there in what's called the ground state, the n=1 state. If a wavelength comes by, just the right wavelength, it will excite the electron, and it will move up. It can move up to higher energy states. It can move up to the n=2 and n=3, depending on the wavelength that it gets. Wavelengths that are too low that it doesn't like, it ignores. Wavelengths that are too high, it doesn't like, it ignores. But when it gets wavelengths, specific ones that it likes, there's one wavelength that'll move it up to the number 2 level. There's one wavelength that'll move the electron up to the number 3. And there's more levels. Then after some time, because the electrons want to be near the proton, they will come back down. They don't have to come back down all the way to 1. They can go from, say, 4 to 3, or from 4 to 2, or 4 all the way to 1. When that happens, now those photons are released. But because their hydrogens are moving around, they can be released in any direction. But the light coming, here's the sun, here's Earth, the light that was coming from the sun, well, at the surface, the hydrogen is absorbing certain wavelengths because it likes those wavelengths. The electrons go up to higher levels, then they come back down, so you get that energy back, but it's in any direction. The bottom line is Earth doesn't get it, and that's why we have those dark lines, so we don't get a whole bunch of the wavelengths. Helium is the same. Notice though that helium, right, there's 2 protons, so the electrons go a little bit closer. So it also has different excited states where the electrons can go. But notice they're different from the hydrogen. Boron has 5 protons, so the electrons can get even closer. But notice that these are different. Guess what? For all of the elements, is my face blocking this whole thing? I hope not. Oh my God. Well, you can see it now. So if it was blocking, you can see it now. Here's hydrogen, here's helium. Let me check. I don't want to go through this whole thing and I blocked everything.